Hello, hi, welcome. What I wanted to talk about today is a sort of introduction to AI and machine learning. So first off, AI. The definition itself of artificial intelligence has varied over time and is quite vague, but generally we can consider that it started with the development of the computer after the Second World War. And what might surprise people today is that already back then there was talk of making conscious programs, conscious computers. One family of AI programs that saw a lot of success really quickly was expert systems, where the task is defined as a series of rules to solve. And so this is great for every problem that might be hard for a human to do, but not that hard to describe. So you could think of chess, for example, 97 IBM's Deep Blue beating Kasparov, on any other system that can work on predefined rules such as laws. However, there are many tasks that do not fit under this category of simple to describe but hard for a human to do. And opposite to that is any type of task that is very intuitive for us to do but hard to describe, or demands a lot of other external knowledge. Any task related to text or images can often require a lot of external knowledge. When we look at a picture, for example, we use our knowledge of human anatomy, animal anatomy, geography, lighting, perspective, and so on. Expert systems basically require having a pre-formulated answer to the problem, and that is where machine learning comes in, which got really popular around the 90s. The mathematical algorithms that are behind machine learning are much older, and now in machine learning the decision strategy itself, how the problem is solved, is dependent on a dataset. And so the program basically makes a model that has learned from experience how to solve the task. If you think of mathematical functions like a linear regression or a logistic regression, you have, for example, x plus b. From the moment that a and b in that formula are obtained from looking over a dataset and minimizing some kind of error, that is machine learning. The moment that a and b are prescribed by any reason, then it is an expert system. For example, a real estate company looking to build a model that would predict what is the price that they should sell a specific building for might build a dataset over the history of activity that tracks a few variables, probably more, and then the price. And so a machine learning algorithm will take these five variables over 1,000, 2,000, 3,000 examples, and we'll use it to create the optimal model that solves for the price. Now, one of the main issues of doing things this way, what we call classical machine learning, is that you have to hand design features to fit the problem. So in some tasks that can be easy, but in some other tasks that can be much more complicated, if not more complicated, than the task solving itself. So one subfamily of machine learning is representation learning. For a quick example of what we mean by representation, these four equations are the same, and yet naturally the Arabic one would be quicker to solve for most people. And so the point of representation learning is how to learn from a dataset what is the best representation that could then be solved by an algorithm. And so now the creation of features is part of the learning process, and out from human hand and human design. One typical example of a representation learning task would be an autoencoder, which is any type of model where the dataset is used to learn an encoding function that encodes a learned representation, and another function, a decoding function, is used to recreate the same data only from the learned representation. One subset of representation learning is deep learning, starting just before 2010. Here the strategy for learning the right representation is to learn complicated concepts by learning a bunch of smaller, simpler concepts nested in one another. Today this is where we find most neural networks, especially large, very large neural network models. Deep learning algorithms are the ones that are really making themselves heard in recent media of the past 10 years. With this strategy, raw data can be directly fed to the model, such as images or text, and the model can learn directly from the raw pixel values and so on, exactly what it should look at. This is a simplified example of a computer vision deep learning model where the image is fed raw into the model. So the input is just the raw pixel values, and then over the the following layers, the model can learn exactly what kind of variables, here visual patterns, it wants to look at. About a year ago, a new subcategory was proposed called foundation models, and that have been traced back to around 2018, such as all the GPTs, BERT and CLIPS that you may have heard of. The particular characteristics of these models are their extreme size and their training paradigm. These models are not trained on one specific task, but rather are trained to optimally transfer to as many tasks as possible. Such as, for example, learning essentially what is text, what is language, what is human writing like, or what are images like, to then be able to very easily transfer to a translation task, a question answer task, and so on and so on. And from GPT-3 onwards, including especially ChatGPT, we can see that the transfer to the downstream task is so easy that it can be fully put into the prompt. If you ask ChatGPT translate this, it can do it, even though this is the first message of your discussion with it. These models are also increasingly multimodal, meaning they can take, for example, text and images for every text-to-image generator that we've seen in 2022. I think it's now very useful, if not necessary, to include them into the discussion and presentation of what is AI currently. These are the models that, to me, have really exploded in popularity and discourse around AI recently, especially since 2020. And these are the main ones that have the most potential and the most risks altogether. On the topic of risk and as a sort of summary over this whole thing, I'm going to use this image from the report on foundation models. In this image, they plot the various fields over a growth of emergence and of homogenization. So first we have expert systems and knowledge bases for any kind of task that is easy to describe to a computer, such as, for example, playing chess or most, if not all, game AIs to this day. Then, really popular in the starting from the 90s, is machine learning, where we now learn how to solve the problem from a dataset. And in terms of homogenization, now many people use the same learning algorithm to solve very different tasks. As long as you can describe your tasks in a few hand design features, a linear regression will always work. Then representation learning decides to tackle the problem of hand design features by learning them from data. And in particular, deep learning decides to learn features through a combination of many simple features. So now nothing is specified, there's just the input data, and everything is learned through the learning process of a specific dataset. This in turn means that many different problems can now be solved with the same feature extraction plus task solving process. From foundation models emerge the functionalities, as they essentially have so much insight on the data they've been fed that they can be asked on the fly to create any type of task, even if they have not been explicitly trained to solve it. Foundation models further reinforce the homogenization of deep learning, where instead of any task using a kind of neural network, they may now be using the exact same, not only type of operation, such as convolution or transformer, but also the exact same type exactly of model, where for a while, for a few years, every model that came out that treated text was based on BERT. Now they might be based on GPT, who knows. And to me, this approach illustrates pretty well what should be remembered about these main categories. As we go further from left to right, there is a higher performance ceiling from not being bound to human error and being able to learn more and more of every insight that is in the data. But there is also more risk of being affected by a poor dataset, also more risks in terms of social issues. I do want to insist though that these different categories still have their own use of application, should not be regarded as a chronology where new category replaces the old one. For a new generic task today, you would ideally be able to evaluate exactly all these models